Since we're done with our discussion on double integration, we are now ready for triple integrals. How do we evaluate triple integrals? Now, if we will consider a solid, okay, and just imagine dividing the solid into rectangular bags. Okay, instead of a rectangular parallelepiped in double integration, we will have it this time as a rectangular box. The rectangular box whose sides are dx, dy, dz. So, for example, if we will consider this as the element, which is a rectangular box. Okay, we shall call this as dy. This side is dx, and the height is the differential of z. And if we will get the volume of the rectangular box, the rectangular element, then the rectangular element is the differential of v, which is equal to dz dy dx if it is vertically simple, or we can take the differential of v is equal to dz dx dy. Okay, when we are doing application. But of course, we can have the other four iterations of the differential of v. Okay, the four other iterations, of course, are dy, dx, dz. Okay, let us write it here. Okay, we can have also the iteration dy, dx, dz, dy, dz, dx, dx, dy, dz, and dx, dz, dy. Okay, but of course, depending on whether the region G is rectangular or non-rectangular. Okay, but if it is rectangular, the region G is rectangular, then we can use any of the six iterated integrals. Okay, but if the region G is non-rectangular, then it is limited depending on the given function, of course, okay, the boundaries of the solid. So just as a double integral can be evaluated by two successive single integration, a triple integral can be evaluated by three successive integration. So instead of we have a double symbol of integration, we will now have triple symbol of integration. And the triple integral of a function f in x, y, and z over the region G is the integral of f of x, y, z times the differential of v, okay, over the region R. Okay, the triple integral over the region G rather. And if we will imagine, okay, the solid, okay, please look at the green solid, okay. Imagine that there are infinitely many rectangular boxes here, okay. And if we will take one of the representative rectangular box, of course, okay, the volume of the box is equal to the differential of V, or delta V sub k. So therefore, the volume of the box is equal to f of x sub k, y sub k, z sub k times delta V, okay? And if we will get the summation of the volume of the boxes, okay, where k goes from 1 to n, and getting the limit as n increases without bound, then that is the triple integral of f okay, times the differential of V. So if G is a rectangular box defined by the inequalities x going from A to B, y going from C to D, and z going from K to L. And if f is continuous on the region G, then the triple integral of f of x, y, z times the differential of v over the region G is the triple integral of f of x, y, z dz dy dx, where z goes from k to l, y goes from c to d, and x goes from a to b. Now, the iterated integral can be replaced by any of five other iterated integrals that result by altering the order of integration. Okay, just like what I have written here, we have the different order of integration by altering the iterate the order. Okay, so we have dy dx dz, dy dz dx, dx dy dz, dx dz dy, dz dy dx, and dc dx dy. So there is no problem if G is um, considered as a rectangular region. Okay, but of course, there will be limited iterated integrals, no, limited order of integration depending on, as I have said earlier, the boundaries of the solid. So to illustrate how to evaluate triple integrals. First example on how to evaluate triple integrals. In double integration, okay, let us say the order is dx dy. Okay, we perform the inner integral first, no, with respect to a variable, and the other variable is temporarily held as constant. Now, similarly, in evaluating triple integrals, okay, just like in the first example, when evaluating the inner integral in z, where z goes from 0 to 1, the other two variables, y and x, are temporarily held as constant. And the result of the innermost integral becomes the integrand of the next integral in y, okay, which goes from 0 to 3. Then we evaluate the integral in y. Okay, the result will be the integrand of the outermost integral in x, okay, where x goes from 0 to 2. So that is how it goes, just like in double integration. Okay, hence, if we will evaluate the triple integral of x, y squared, z squared, dz, dy, dx, where z goes from 0 to 1, y goes from 0 to 3, and z goes from 0 to 2, then we evaluate the innermost integral in z. So this will give us, okay, the result after evaluating the innermost integral will give us double integral, okay, where y goes from 0 to 3 and x will go from 0 to 2. Okay, so evaluating the integral of x, y square, z square, since we are evaluating the integral in z, x and y are temporarily held as constant. Hence, xy squared is held as constant. And the integral of z cubed dz is z to the fourth, okay, excuse me, integral of c cubed dz is c to the fourth over 4. And we are going to evaluate this, okay, from z is equal to 0 to z is equal to 1. And do not forget to write dy dx here. Okay, hence, This will give us the double integral, okay, y going from 0 to 3, x going from 0 to 2, and evaluating z to the fourth. Okay, take note again that x, y square is constant, and we can write 1 over 4, okay, here, okay. What I mean is we can factor out xy square over 4 and just evaluate c to the fourth, okay, from z is equal to 0 to z is equal to 1. Okay, hence this is equal to the double integral, okay, y going from 0 to 3, x going from 0 to 2. When z is equal to 1, then that will give us, let's write 1 over 4 before the integral sign. So we will have xy square. Okay, when z is 1, that gives us 1. And when z is 0, that will give us 0. C to the fourth is 0. Then dy dx. So the resulting integral is 1 over 4. Okay, we write the constant 1 over 4 before the integral sign. Okay, y going from 0 to 3, x going from 0 to 2, and we will evaluate xy square dy dx. Okay, so this time we will evaluate the inner integral in y, and x is temporarily held as constant. So we have 1 over 4 integral from 0 to 2, and holding x as constant, integrating y squared dy will give us x times y cubed over 3, and y will go from 0 to 3. Okay, times the differential of x. Now we can again write 1/3 before the integral sign. So that gives us 1 over 4 times 1/3. Excuse me for a moment. Okay, times 1/3 integral from 0 to 2. Then we have x, and we shall evaluate y cubed. Take note that x is temporarily held as constant. So we will evaluate y cubed from y is equal to 0 to y is equal to 3 times the differential of x. Hence, this will give us 1 over 12. Okay, 1 over 12 times the integral from 0 to 2. Then we have x. Okay, evaluating y cubed when y is equal to the upper limit 3 will give us 27. And when y is equal to 0, y cubed of course is 0. Okay, and we have 1 over 12 integral from 0 to 2 of 27 x dx. Now, since 27 is a constant, we can write 27 before the integral sign, and we can do simplification by cancellation later. And then evaluate the integral of x dx from 0 to 2. Okay, so by cancellation, okay, 27 and 12 are both divisible by 3. So 12 by 3 will give us 4, and 27 by 3 will give us 9. And integrating the integral, integrating x rather in, okay, or integrating x dx, okay, gives us 9 over 4. Integral of x dx is x square over 2. Okay, and we have to evaluate this from the lower limit x is equal to 0 to the upper limit 2. Okay, let us again write 1 half, or we can evaluate at x is equal to 2. So 9 over 4 times getting the value of x squared when x is equal to the upper limit 2 will give us 2 raised to the second power, which is 4, divided by 2 will give us 2. And x squared over 2 when x is 0 is 0. Hence, we have 9 over 4 times 2. And by cancellation, it gives us the integral rather is equal to 9 over 2. So we were able to evaluate the triple integral in z, y, and x in that order, no? Okay, where z goes from 0 to 1, y goes from 0 to 3, and z goes from, x rather, goes from 0 to 2. So we were able to uh, do the iterated integral. We evaluate the innermost and then the next innermost and then outer integral. So I hope that you were able to follow the evaluation of triple integral. Okay, so this time we will consider example number 2. Okay, this time it is not a rectangular region G. Excuse me for a while. We are going to evaluate the integral in the order dz, dx, dy. Okay, where z goes from 0 to 1 minus x squared, x goes from negative 1 to 0, and y goes from 0 to 2. Hence, we will evaluate the innermost integral in z. So we write here double integral, okay, y going from, negative, x going from negative 1 to 0, y going from 0 to 2. And if we will evaluate the integral, the innermost integral, okay, with respect to the variable z, x and y are temporarily held as constant. So we take x, y as constant, and we evaluate z dc. Of course, the integral of z dc is z squared over 2, and we shall evaluate this from the lower limit z is equal to 0 to z is equal to 1 minus x squared. Okay. Now, since we have a constant 1 half here, we can actually write 1 half before the integral sign. So the limits of integration, x going from negative 1 to 0, y goes from 0 to 2, and we have x, y, and then just evaluate z squared at the upper limit minus z squared at the lower limit. So the upper limit z is 1 minus x squared, so replacing z by 1 minus x squared will give us 1 minus x squared quantity square minus the value of z squared at the lower limit 0. Of course, when z is equal to 0, then that gives us 0 times the differential of x dy. Okay, so next we simplify So simplifying gives us 1/2. Okay, limit here goes from -1 to 0 and 0 to 2. So we have xy. Okay, getting the square of 1 minus x squared gives us 1 minus 2x squared plus x to the fourth dx dy. And if we will distribute xy in the quantity 1 minus 2x squared plus x to the fourth, it gives us 1/2. Okay, integral from 0 to 2, -1 to 0 of xy minus 2, uh, 2x raised to the third power y plus x to the fifth power y dx dy. So we are now ready to evaluate the integral in x. So evaluating the integral in x, we temporarily held or hold rather y as constant. But please take note here that y is common in each term. So before we evaluate the integral, we can actually factor out y. So if we will factor out y, let's have it here. We have 1/2. Okay, we have double integral from -1 to 0, x going from -1 to 0, and y goes from 0 to 2. So that we will have, excuse me, quantity x minus 2x cubed plus x to the fifth times y. We factored out y. Then we have dx dy. Okay, now please take note also that when we evaluate in x, y is temporarily held as constant. Okay, so that gives us, we might as well write y. Okay, we can just write y before. Okay, so this is dx dy. So we will have y, which is temporarily held as constant. Okay, and integrating x minus 2x cubed plus x to the fifth will give us x squared over 2 minus 2x to the fourth over 4 or x to the fourth over 2 plus x raised to 6 over 6. Okay, and this must be evaluated from x equals -1 to 0 times the differential of y. Okay, so what's next? We evaluate the resulting integral at x is equal to 0, okay, minus x, the value of the integral, the resulting integral when x is -1. So we have 1/2 integral from 0 to 2. Okay, y is constant. And when x is equal to the upper limit 0, everything is 0. So we will have 0 minus. Okay, and when x is -1, then that will give us -1 square is 1. So we will have 1/2. -1 raised to the fourth is also +1. So 1/2. Okay, plus x raised to the 6 when x is -1, then that will give us 1 over 6. Close times the differential of 1. Now, 1/2 minus 1/2 will give us 0. So this will just result to 1/2 integral from 0 to 2 of y times -1 over 6 times the differential of y. But since we have a constant factor in the integrand -1 over 6, we can just write it before the integral sign. And that simply gives us integral from 0 to 2 of y dy, okay, which is equal to -1 over 12 Okay, and the integral of y dy is y squared over 2. So we have y squared over 2, and this must be evaluated from 0 to 2. Okay, hence we have negative 1 over 12. When y is equal to 2, then it will give us 4 at the upper limit 2. So 4 square, sorry, 2 square is 4. 4 over 2 is 2. So we will just multiply this by 2 since when y is equal to 0, okay, y squared is 0. Hence, we have negative 1 over 12 times 2, which is equal to negative 1 over 6. Therefore, the integral is negative 1 over 6. Okay, so I hope that you were able to follow the discussion. Okay, so let us now have, uh, this is actually the last example. Now use triple integral to find the volume of the solid within the cylinder x squared plus y squared is equal to 9 between the planes z is equal to 1 and x plus z is equal to 5. Okay. We already have here the illustration of the solid. Okay, if we have a cylinder x squared plus y squared is equal to 9, then it is a circular cylinder, okay, whose radius is equal to 1. Therefore, okay, we can draw the trace on the xy plane, which is a circle whose radius is equal to 1 and whose center is at 0, 0. So this will give us we can just project it, okay, to have the circular cylinder, okay, bounded below by z is equal to 1 and above by x plus z is equal to 5. Okay, by the way, if we have the x-axis and the z-axis, consider this as the z-axis, and this one is the x-axis. If we have x plus z is equal to 5, the x-intercept is 5 and this is 5, and the z-intercept is also 5. So the plane is this. This is actually the plane, okay, cutting the circular cylinder. And you can see here the upper base of the cylinder, which is the plane uh, x plus z is equal to 5. This is x plus z is equal to 5. And of course, if we will find the solid, sorry, the volume of the solid rather, then we have to draw the element here. So just draw the element. This is the base, okay? And we will simply draw a rectangular box here, which will serve as the element. So on the lower base, just draw a rectangular box. Okay, this is the rectangular box. Okay. Okay, I will just draw the rectangular box here. Okay, and this is dx, dy, dz. The volume of this rectangular box is the differential of V, okay, which can be taken as dz, okay. Then we decide whether it is vertically simple or horizontally simple. Okay, we may take it as dy dz or dx dz. Let us just have it as vertically simple. Okay, dy dz. So going back to the rectangular region R on the xy plane, since we consider the order dy dz, then we can just draw a vertical line, okay, and this is the representative element. So it means that uh, we will go down, up, then left to the right, okay. So since we have a circle, x squared plus y squared is equal to 9, we can solve for y, and then y is equal to, okay, actually we can have this as y squared is equal to 9 minus x squared. So getting the square root of both sides of the equation will give us y is equal to positive square root of 9 minus x squared and negative square root of 9 minus x squared. Okay, the lower end is y is equal to negative square root of 9 minus x squared, and the upper end is y is equal to the square root of 9 minus x squared. Hence, if we will get the volume of the box, okay, let me use the blue ink. If we will get the volume of the box, okay, this box, okay, the volume is equal to the differential of V. Now, if we will get the triple integral or evaluate the triple integral over the region G, okay, where we will take the differential of v equals dz dy dx, then the volume is equal to the triple integral of the differential of z, differential of y, differential of x. Okay, so we can now have the interval in G, okay, in the region, okay, sorry, we use the region R. So the region R, sorry, in the XY plane. Okay, so the region R in the XY plane will give us Y, okay. Y will go from negative square root of 9 minus x squared, negative square root of 9 minus x squared, okay, to positive square root of 9 minus x squared. And of course, x will go from the leftmost, negative 3 to positive 3. Okay, and if we will consider, of course, the region G, we have to include the interval of z, and z will go from z is equal to 1, okay. Take note that the solid is bounded by, okay, z goes from z is equal to 1 to uh, z is equal to x squared plus y squared minus 9. Okay, so, sorry, this should be z is equal to 5 minus x. Okay, so we will solve for c here. C is equal to 5 minus x. And the element will go from the lower base, z is equal to 1, to the upper base, z is equal to 5 minus x. So we can now write the limits of integration. C will go from 1 to 5 minus x. Y goes from negative square root of 9 minus x squared to positive square root of 9 minus x squared, and x will go from negative 3 to 3. Okay, hence we have integral from minus 3 to 3. Then we have negative square root of 9 minus x squared to positive square root of 9 minus x squared. Okay, the integral of the differential of z, okay, which is the innermost integral, okay, is z, and we have to evaluate z from z is equal to 1 to z is equal to 5 minus x. Hence, this is equal to, okay, we have integral from minus 3 to 3, okay, limit of integration in x. Then in y, negative square root of 9 minus x squared to positive square root of 9 minus x squared. Okay, sorry, there must be dy dx here. And when z is equal to the upper limit 5 minus x, then we have 5 minus x minus z, lower limit z is equal to 1, so minus 1 dy dx. Okay, so this gives us, wait, this gives us a double integral minus, or y goes from, sorry, x goes from minus 3 to 3. Y goes from negative square root of 9 minus x squared to positive square root of 9 minus x squared. And if we will simplify 5 minus x minus 1, that gives us 4 minus x dy dx. Okay, and since x is temporarily held as constant, if we will do the inner integral, then 4 minus x is constant, and the integral of dy is y, where y will go from negative square root of 9 minus x squared to positive square root of 9 minus x squared times the differential of x. Okay, hence, that will give us the integral from minus 3 to positive 3 of quantity 4 minus x times. Okay, when y is equal to the upper limit square root of 9 minus x squared, so that gives us square root of 9 minus x squared. Then minus the value of y at the lower limit negative, so negative will give us positive. Square root of 9 minus x squared times the differential of x. And square root of 9 minus x squared plus square root of 9 minus x squared will give us 2. Okay, so we have the integral from minus 3 to positive 3. Okay, so that gives us 2 times 4 is 8. Okay, so 8 times the square root of 9 minus x squared. Okay, then minus x times the square root of 9 minus x squared times the differential of x. So we can express this as sum of two integrals. So if we will express this as sum of two integrals, then we have 8 times the integral from minus 3 to positive 3 of the square root of 9 minus x squared times the differential of x, then minus the integral from negative 3 to positive 3 of x times the square root of 9 minus x squared times the differential of x. Now, the first integral can be evaluated by trigonometric substitution. Okay, and the other integral can be evaluated by power formula. So just continue the integration in x, okay? First integral by using trig-zab, and then later you can actually use the Wahl's formula. And then we have the second integral, which can be evaluated by power. And